Okay, so we're going to move on now to the next chapter. In lecture 8, we're going to start off with graphs of equations, and later on we'll talk about functions and inequalities as well. Okay, so let's get started. So how do we plot points? Well, if I give you a pair of points, right, we have an x-axis and a y-axis, and these coordinates just designate where they belong on this plane here. So the 1, 3, for example, 1 is designating where you're going to be on the x-axis. So that, let's say that we're incrementing these by 1. So if this was 1, this would be 2, 3, 4, 5, 6, and so on. So 1, 3, we're going to go 1 in the x direction, positive 1 in the x direction, and then positive 3 in the y direction. Right, so 1, 2, 3. So that point would be right here. So that's 1, 3. And negative 1, 2, so now we're going to have to go in the negative direction of x. So we would still increment these by 1, but in the negatives. Okay, so negative 1, positive 2, that would be the location for this point here. So negative 1, 2, 4, negative 2, so 4, and then down here, negative 2, so 4, negative 2, and then negative 3, negative 3, so negative 3, and then if you want to label these, you can. It's good practice to at least label a few of them so we can see what the increments should be for your particular problem that you're working on. But if it's clear, it's not absolutely necessary, but it is a good idea to at least label a couple of them. Okay. Negative 3, negative 3. Okay. There are also designated quadrants. So when the x and y values are both positive, like as in this point, this is considered quadrant 1 over here, and usually you write that in Roman numerals. And then you proceed counterclockwise. That's just the convention. So in the negative x direction but positive y direction, this is quadrant 2. Down here, when they're both negative, this is quadrant 3. And over here, this is quadrant 4. I mean, it's not absolutely necessary right now that you actually memorize that. It's just a convention. So you could refer to points over here in quadrant 2. It's just, it's just a convention that can be helpful in certain situations, especially in other courses such as trigonometry. Okay, so moving on. So that's how you plot points, but how do we graph functions? So how do we graph functions? Well, the equation is designating sort of the algebraic relationship between these variables, but the graph can give you a visualization of that relationship, and it can be very helpful. So the technique that is quite common is, well, later on you're going to look at this and see that that's actually going to be a line. But at the moment, what is the technique? It's you create a table. All right, so you're going to create a table of x and y values. Okay, now the way that this equation is written, we can think of the y values depending on the x values in the following sense. So let's say that I pick some arbitrary x values here. So let's say that I pick, say, negative 2, negative 1, 0, 1, and 2. So what I'm going to do is for each of these x values, we're going to compute what y must be so that this equation is valid, right? So over here, see, y is equal to, what is y equal to? It's equal to 2 times this x value. So that would be negative 4, right? So what you're just going to do is multiply the corresponding x value by 2. So we'll get negative 2. 0 times 2 is 0. 2 times 1 is 2. 2 times 2 is 4. Okay, so you're sort of writing out your pairs of points here. So you see that this now gives us a pair of points, -2, -4. And what we can do is pretty much what we just did above, which is plot these corresponding points and see what happens. Okay, so this gives us a pair of points. You don't have to write this out. I'm just trying to connect what was done up above. So -1, -2, because you can see the pairs right here, 0, 0, 1, 2. So that's sort of the advantage of writing out this table. And we can plot these points, right? So the easiest one to plot would be 0, 0. And convention is that 0, 0, we call that the origin, right? So 0, 0, 1. So let's say that I'm incrementing these by 1 again. So 1, 2, and so on, right? 1, 2. You don't have to label all of them. It's just, do you see that once I designate the incrementing, it's just, you can see what the convention is. You know, sometimes you might want to increment by 2s or 3s if you know that the values are going to be much larger. But in this case, they're pretty small, so I can increment by 1s. So, so we plotted 0, 0. What about 1, 2? So 1, 2. It's right here. So we plotted that one. 2, 4. So 2, 4 is that one. -1, -2. So -1, -2. And -2, -4. -2, -4. Okay, now this equation is supposed to be valid for all x and y values. So these are some x and y values, but you see, I didn't include all of them. So for example, there are many, many other points that this equation satisfies. And the way that you essentially designate that is you sort of fill in these gaps, right? So the actual graph will be this picture here. So connect your dots, and it will continue this pattern. Try to draw that as accurately as I can. And it will go on forever. And so there's actually infinitely many points on this line that satisfy that equation there. But that's how you graph them, and that's a very good general strategy. If you can't recognize what it is, you can always build this table, and that is a very, very useful strategy. So let's continue on to another example. All right, so let's graph 3 things in one graph. So we're going to graph that equation, this equation, and this equation. So we could actually use the same technique as above. So we'll have x values and y is equal to 3x, right? So we can start to pick some arbitrary x values, maybe -1, -2, 0, 1, and 2. So plugging this in, so we're going to multiply all these by 3, so that'll be -6, -3, 0, 3, and 6. Okay, so if we plot these, looks like we have 0, 0, so that's the origin. 1, 3, 2, 6. Right, and here I'm incrementing these things by 1s. So I'll label a couple of those just so that's clear. -1, -3, -2, -6. Okay, so this equation right here, this first one, is going to be all the points on the red here. Now, of course, it should be a straight line, but I'm drawing with this pen and didn't quite work out so perfectly, but that should be a straight line. Okay, what about this one? Well, this one is actually just the equation where x has to be -2. So you actually could use this strategy again, but do you see that this, if you think about this, you're thinking of that as, you know what, let me switch to a different color. Maybe blue. Okay, so this right here, this is going to be the set of points x, y, such that x is equal to -2, right? And what values are those? Well, you can set up, I mean, can you think of some points that satisfy this equation right here? Well, certainly. -2, and then now fill in that blank with whatever you want. That's the only restriction that this equation is giving us. So for example, -2, 0, -2, 1, -2, 2, and so on. So there's going to be also infinitely many points. So what would that look like over here? So plotting this, so -2, 0, -2, 1, -2, 2. So you see, you're just filling in all the points where the x value happens to be -2. See that? So in a situation like this, when you have x equals a constant, like that one, what kind of line are you getting? Well, you're getting actually a vertical line. And why is that? Well, vertical lines are when the x value is fixed, like this, but the y is allowed to change. Okay? So let's look at a similar situation. Here we have y is equal to 4. So let me switch the color again. Maybe purple. Okay. So for this one, what's happening? Okay. Well, you can probably guess that you're actually going to get a horizontal line, because here the y value is fixed, but the x values are allowed to change. So this will be a horizontal line. But why is that? Well, that's the set of points. The set of points xy such that y is equal to 4. So that would look like this, right? X can be whatever you want, but we just have to make sure that the y coordinate is 4. So for example, we could have 0, 4, 1, 4, whoops, 1, 4, 2, 4, and you can also have negatives as well, right? But 0, 4 would be here. 1, 4 would be here. 2, 4 would be here. And then everything on that purple line right there is a point of this form right here. So it's a point xy such that the second coordinate is a 4. Okay, so that's a good thing to remember. When you have x values equal to a constant, that'll be a vertical line. When you have y equals a constant, that'll be a horizontal line. Okay. Okay, so continuing on. So this next question is find the intercepts and graph the equation y equals -1/2 x plus 1. Okay, so what are the intercepts? So the intercepts are the x and y intercepts. Okay, so what are these? So the x intercept, this is where the equation meets the x-axis, right? In other words, it intercepts the x-axis. Okay, whoops, axis. Okay, so that's going to be a point of what form? Well, if you're hitting this x-axis, what do you notice about the points that are on that x-axis? Well, they have a coordinate. So for example, let's say this is 1, 2. For example, this point right here, what are the coordinates for that point? The coordinates for that point are 2, 0, right? And the coordinates for this point are 1, 0. So for all the points on the x-axis, the y coordinate is 0, but the x value is something. And that value right there is our x-intercept. Okay, so where the equation meets the x-axis, so we can say x is equal to that value there. Okay, and same thing with a y-intercept, except it's where it meets the y-axis. Okay, so where the equation meets the y-axis. And there, you'll notice that the x values are 0, but the y values are changing. So there, the x value is 0, but the y values are changing. And so you can use this strategy to actually figure out where they actually are. Okay, so to find the x-intercept, I want the y to be 0 and the x to be something. So what I could just do to find the x-intercept is just set y equal to 0. So if I have, so for the x-intercept, this equation up here, right here, we're just going to set y equal to 0 and solve. And that will give us our x value, and that's where the x-intercept is. So bring the -1 over here by subtracting, right? So subtract -1, and so we have -1 equals -1/2 x. And then now what are you going to do? You're going to, well, I mean, you could divide, but you could also multiply both sides by -2. And so we'll have 2 equals, and then -2 times this will give us 1, which is x. So that's our x-intercept. Y-intercept, so we actually plotted the x-intercept right here, right? So that'll be at 2, 0. That's the point. So it's already plotted. Y-intercept, so let's plot that. So what are we doing there? So y-intercept, where it hits the y-axis, the x value is 0. So let's set that equal to 0 and see what happens. Well, I'm going to have y equals -1/2 times 0 plus 1. Well, anything times 0 is 0, so that's just y equals 1. So then our y-intercept, the point, will just be 0, 1. So we'll put that here. So 0, 1. Right? So 0, 1. And you'll see this right here, as we talk about lines a little bit more, lines are actually completely determined by 2 points. So those are actually 2 points that would be on the table that we could use to actually graph this, right? So if we make a table for this real quick, right? So x, y, okay, and let's say that I pick the x values, -2, -1, 0, 1, and 2. We already actually have 2 of these values, right? So at x equals 0, y was 1. At x equals 2, y is 0, right? But let's fill in the rest of these real quick. If you plug in -2 up here, you'll get 1 plus 1, so that'll be a 2. And if I plug in -1, then we will get +1/2, so that'll be 1.5, so 1.5. And if we plug in 1, you're going to subtract 1/2, right? -1/2 plus 1, so that'll be 1/2. So that's 0.5, or you could just write 1/2 if you want. Okay, and if you plot all these points, you'll see that it'll actually be this line here. So let's just check that real quick. So -2, 2. So -2, 2. Indeed, it is on that line, actually. All right. Now, at the moment, we haven't really discussed lines in general, but I think it's good to kind of think about these things. And one property that lines have that's very good is once you have 2 points, like the 2 points that we have here, it actually is enough to determine the entire equation. All right, so we'll talk about that more, but the rest of these points are on that line. -1, 1.5 is right here, and then 1.5 is right there. Okay. Okay, so let's continue with this. So let's find the intercepts and graph this equation here. So the x-intercept right? So when we're hitting the x-axis, the y value is 0. So let's set y equal to 0 and solve. Okay, so what are we going to do? We're going to add 9 over here. And so then we have 9 equals x squared. Okay, now here's where we encounter something interesting, right? So normally we just do sort of the basic operations in order to finish this equation here. But it turns out that if you have this square and we're trying to solve for x, well, we have to do essentially the opposite operation to get rid of that square. And what would that be? Well, if you took the square root, then it seems like the appropriate operation, because if I'm squaring something, then to undo that I would have to do the square root. However, what's interesting about doing that operation is you actually are introducing multiple solutions, because let me just show you the convention that you do. So if I take the square root of both sides, when you take the square root of an actual number, this is always going to be just the positive square root, whatever that should be. So that is 3. And that's because 9 is, because 3 squared is 9. So the square root of that would be 3. But when you take the square root of a variable squared, and we don't know the actual value of that, then this ends up actually being the absolute value of x. All right? So what would the actual value be then? Well, we know from solving absolute value equations like this one that if you want to get rid of the absolute value, that you will get plus and minus this solution here. So we actually have 2 intercepts, which is quite different from the example up above. So the intercepts are x's plus 3 and minus 3. So what are the points actually? So the points are 3. And then if I take 3 and I plug that in, you'll have 3 squared minus 9. So 3 squared is 9, so 9 minus 9 is 0. Right? So in other words, I just did the double checking. We already know the x-intercepts are going to be when the y-coordinate is 0. So at 3, so if I increment these by 1 again, so we're going to have this point right here. Right? So that's our 3, 0. And then we're also going to have a -3, 0. Okay. All right. Just so you know, at this point, for future solutions to such a thing, you could alternatively, if you don't want to write this absolute value step, you could write plus or minus the square root of 9, and that's equal to x, but I think it's good to actually see all the steps here. Okay, so for the y-intercept, what are we going to have to do for that? Well, y-intercept, we have x is equal to 0, so y is going to be 0 squared minus 9, and that's equal to 9. And so again, the x value is 0, so the point is 0, 9. Oh, sorry, minus 9. Minus 9. Okay, so 0 minus 9. So I guess, I've incremented the x values by 1, but since 9 isn't going to cut it here, maybe we should increment these by the y coordinates by 2. So I guess this brings up a good point. It's sometimes a good idea to not choose your increments until you realize what kinds of values you're going to be working with. So -2, -4, -6, -8, -10, right? It's perfectly fine that you can increment these differently. Just be consistent, okay? So -9 would be down here. So that would be our y-intercept. So that is 0 minus 9. Okay. And then now, so this is quite different from the line, right? So when we had the above examples, when we were graphing those equations, they were lines, they were straight. But look, now we have to connect these 3 points. And how do we do that? Well, we know that this equation is going to pass through those points because these points satisfy that equation. So to kind of fill in the gaps, you could find a couple other values, and that's where the table can really give you this advantage. All right. So x, y, we have a few values, but maybe let's do we already have -3, 0, right? We already have the two other ones. So let's fill in the gaps here. So 1, 2, 3. Right, we already have 0 is -9, and we also have 3 is 0. But we could also figure out all these things just by plugging them in. So if I plug in -2 squared will be +4. 4 minus 9 is -5. Plugging in -1, that'll be 1 minus 9, so that's -8. 1 squared minus 9 is -8. 2 squared is still 4. And then subtract 9, we should have -5. So we will actually, you see there's a symmetry here. So -2, -5 will be down here. And then -1, -8 is like this. And then 1, 8 will be that point there. 2, -5 is here. Okay, so you know what? Let me switch to another color since everything is labeled with red. So let's actually graph this. Okay, so let's fill in this information here. So we're going to connect those red dots together, and that would look something like this. All right, so I'm going to do my best, but bear with me. Okay, so it'll look like this. Later on, we'll work with these things a little bit more. This is an example of a parabola. Okay. Okay, so continuing to the last example here. So let's find the intercepts and then graph this real quick. So the x-intercept. In that situation, y is going to be 0, so let's solve that. So 0 is equal to -1/3 x. And to solve this, we could multiply both sides by -3 to cancel this out. So we'll have 0, and then -3 times -1/3 will be a 1, so we're just left with x. So our point is actually the origin. And for the y-intercept, there, the x value is 0. So we're going to have y is equal to -1/3 times 0, which is y equals 0. So that point is also the origin. So this is an interesting example because the x-intercept and y-intercept points were actually the same, which could totally happen. That's fine. We'll also see other interesting situations, like you might have an equation that doesn't have any x-intercept. So we'll encounter these sort of situations as we learn a little bit more. So let's graph this real quick. We could use our table method. Okay, now if you kind of think about this, the values that I'm going to plug in, let's say that I choose 0, 1, 2, 3. So I'm going to get some fractions there. But if I pick something like 3 and -3, then I'm going to get some nice reduction. So it might be a good idea to enlarge the region or pick different points depending on the type of function that you're actually getting. So just to kind of illustrate that, I'm going to go from -3 to 3. So plugging in -3 for x, right, what are we getting? Well, the 3's cancel or reduce and the negatives cancel, so I get +1, right? You know, if you're ever worried that you're not pairing the numbers right, you can fill in with horizontal lines here. So -2, plugging that in, you will get 2/3. Plugging in -1, we'll get 1/3. Plugging in 0, we get 0. We already saw that. Plugging in 1, we will get -1/3, -2/3, and then plugging in 3, we're going to get -1. Okay, so let's plug in the nice values. So -3, -3, 1. Right, so -1, -2, -3. So -1, -2, -3, 1, 2, 3, 1, 2, 3. Okay, so -2, 2/3, and then oh, sorry, I plotted that point wrong. So -3, 1 is going to be where? So -3, but then +1, right? Is right here. So -3, +1. All right, and then -2, 2/3 is about there, and then -1, 1/3 would be about there, and 0. So then let's plot 3, -1. 3, -1 will be here, and so we're going to fill in all the points in between, and we're getting it looks like a line again, right? So let me switch to a different color to illustrate that. Okay, so let's fill this in. Graph that information. So it looks like you're going to get this line here.